Now let us discuss about how we can access those memory, especially for data writing, right? The write into some part as global or variables or external variables, means the static data part, and also how we can write into the stack area, dynamic areas. We won't be talking much about the dynamically allocation like heap part of the dynamic data, this new malloc, etc. Those are more part of your operating system study, how the memory is managed. For the dynamic allocation, we'll be talking more about stack usage of the dynamic allocated area and also the static data area, and we need to see how we can access those area for reading and writing, right? Text part, we don't write it usually. In this class you never have to write into the text area, right? When you assemble a program in the MIPS environment, is basically assembles the machine code and copy it onto your text part, that area. But think one interesting point, if you through your program, if you write into the text part, which I'm pretty sure assembler as assembler it will not let you do that, at least directly. You can do some indirect writing there, but again, like, just experiment, okay? uh, the implication of that, like if you are writing into the text part from within your program, you are actually writing a self-modifying code, which is very interesting topic in computer science area, right? A program is morphing itself, okay, morphing itself into something else. So that's very interesting. So you can do that at least at this level. You write a program and which writes into itself, generate itself some code to morph its behavior, okay? So that's interesting, but okay, beyond our discussion, beyond our scope of discussion in this class, okay? So we'll restrict ourselves to read and write in the static and dynamic data. So dynamic data area, that too we will be interested into accessing as a stack, okay? So MIPS provide only one variant of address computation for read write, okay? So each read write, you need to tell the whole system that which address you want to read or write, okay, read from or write to. That address computation may have a different variants, okay? How we giving the address directly, are we giving address indirectly, and so on and so forth. One such variation is called displacement addressing. What is meant by that? It start with a base address and then you do some arithmetic manipulation on that address value, like adding an offset. It's always not adding. If it is a negative offset, it is subtracting. So you can, from a base address, you are computing your final target address by adding an offset, okay? And this offset can be positive or negative. So if it is a positive, then you are going to access some higher address value from the base address, or you are, if it is a negative offset, then you are going to access lower address value from the base address. So that's the idea of your displacement addressing. Target address then is basically is the content of a register in case of MIPS. So you can store some 32-bit values in the MIPS. So and you can use it as your base address and then assign extended immediate 16-bit encoded in the instruction. So essentially load and store, these two instructions are I-type instruction where it has opcode RT, RS and or RSRT. It's I don't remember exactly what format. Please refer back to the older slide. And then a 16-bit immediate value. And that 16-bit immediate value is used in a sign extension context. What does it mean? A register is 32 bits, right? you cannot do a 16-bit operation with a 32-bit. You need to extend your 16-bit into a 32-bit value. So that extension for this memory computation happens in a sign extension form so that it does not change the value. If you apply minus 16 into that 16-bit 2's complement form, after extension to the 32-bit, its value still will represent minus 16. Okay, so this is what the sign extension is. The format for loading a value from a memory to a register is this, like LW stands for load word. Then you are giving a target register into which you are loading your value, like it can be any register, S0, T0, etc., etc. And then you are telling an immediate amount, this is the offset, 16-bit offset value. And then you are supplying a base register name, like it can be again any ST, any register basically. Okay, no one is imposing any restriction on you to not to use any of the register. But remember, like in last lecture we talked about also register usage convention. Okay, if you don't follow the convention, you probably are going to hit some like some unknown issues there, because the rest of the software system is basically assuming that convention of the register usage. Okay, so use the register with the convention and you can use any registers there. So these registers within this round brace is contain your base address. So that base address will be added up with this offset value, which is you are encoding into the machine code as a 16-bit 2's complement form. So what does it do? Load word is this. Okay, this like formula or this expression looks scary at the first glance, but understand each bit of it. Okay, so then it becomes clear. So R of RT, what does it mean is this: my register content of this RT register is going to be my whatever in my right hand side of that expression, and right hand side says that M square brace close square brace, right? So that means memory at certain address. All right, now this address is calculated by your R of RS, means content of the RS register, okay, whatever you are supplying in that load word instruction, plus the immediate 16-bit value is get sign extended and added to that value that RS content, and that becomes your memory address that you are accessing from. Okay, so that's the one. Okay, let's go to the more scarier expression here, which is related to the load half word unsigned. So half word unsigned means you are loading, you are reading from the memory. Memory is giving you 32-bit, a complete word from it as a device, electronic device, but you are using lower 15-bit of it, that 32-bit value read from the memory, lower 15-bit, it going to the lower 16-bit, like not 15-bit, 16-bit, lower 16-bit value of the entire 32-bit read from the memory is going to the lower half of the RT register and upper half being filled up with 16-0. So this 16 tick B0 means I am having 16 zeros bit, 0 bit, okay, and followed this comma followed by the content I read from the memory. Okay, content I read from the memory, open square brace, close square brace, content I read, I take 16 bit of it, like 0 to 15, 16 bit of it, and use that as a lower half of this RT register, my target register, where I am loading this value. Okay, so half word unsigned means I am just putting like 16 0 at the upper half of the RT register, and lower 16 bit is coming from the memory reading of 32-bit data, and I'm picking up 16 lower bit of from that reading and putting it into the RT register. Within this square brace around related to the memory sign M is basically nothing but your memory calculation, address calculation. See, it's the same as the previous load word. It's a R of RS and sign extension immediate, and you add them up and you get the target address from where you are reading this. And then special on this LHU is this, you are just doing 16-bit, picking up first 16-bit from that 32-bit rate from the memory and putting into the lower 16-bit of the target register RT, higher 16-bit of the RT being 0. There is load byte as well. So we still read 32-bit from the memory location, and out of that 32-bit we pick up 8 lower bit, and rest higher 24-bit of the target register is filled up with 0. 24 tick P0 represents 24-bit zeros, okay, on the higher part, and then it is comma, let's think of as a concatenation with another 8-bit which is coming from the reading of the memory. Address is computed by R of RS, and then sign extension immediate value, add them up, we get the address, we read that address, get 32-bit and pick up 8-bit from that 32-bit and store it in the lower 8-bit of the RT. So that load byte unsigned, LBU, LW, LHU, LBU. Okay, these are your loading operations. Okay, loading operations. It's not end here. We have more. Here. Okay, to load values to the register from the memory, it still continues. There is signed loading also, signed half word and signed byte. Why there is no signed word? Because word is full 32-bit. You are just doing all the 32 bits loading, reading from the memory from a starting address, consecutive 4-byte is read, returned to the processor. Whole 32-bit is kept into the register. There is nothing like a sign. If that value is treated as signed, you treat it as signed. That value is treated as unsigned, you treat it as unsigned. Okay, so that 32-bit has nothing to do with sign notion. So there is no like a signed word and unsigned word loading. But anything below that, like half word or byte, that has a signed notion, right? We cannot mess up with a value if we want to treat it as a signed value. Okay, remember like unsigned and signed, like same bit pattern, we can actually treat as a signed unsigned, but it's really depend on what usage you are doing. Let's try to understand what this is signed half word means. It means that first of all, I cannot blindly, as I do for the load half word unsigned and load byte unsigned in the previous slide, see blindly I am putting zeros onto the upper half, right? 16-bit or 24-bit, because it's an unsigned. But if my intention is to make a sign value loaded, like a half word sign value or byte sign value loaded, that means I cannot blindly place zeros onto this part, higher part. If it is 0 on the higher part, by 2's complement convention, the value is positive, right? Then how can I make a negative value, half word negative value or half word byte value loaded into my register? How can I do that? To do that, we need to make a little more complex operation, at least notation wise, a little bit more scary and the expression we are giving in this area, but be with me and try to understand each part of it. So what load half word sign really does, first of all, it does the memory address computation. So that's common for everything. So don't be worried about that. That is the common thing, right? Then what we are doing here is telling this whole thing is really you are replacing the higher 16 bit of the register RT with the 16th bit of the memory read 32-bit read content. The 16th bit I'm replicating it. I'm kind of replicating. So if the 16 bit of the 32-bit read from the memory is 1, I replicate 16 1 in the higher part of the RT. If that 16 bit is 0, then I'll replicate 16 zeros on the higher part of the RT. The lower part being actually the same thing as we did for the LHU. Means we are just picking up for the lower part this lower 16 bit out of the 32 bit read from the memory. Lower 16 bit we are picking up and putting in the lower 16 bit of the RT. Only trick in the upper part for the signed values. For the signed half word loading, what we need to do is take the 16th bit of the 32-bit read from the memory and replicate it 16 times to the higher bit of the RT register. Now, if we are okay with this concept, then LB load byte signed, that operation is also should be clear to us. Instead of 16-bit replication of the 8th bit of the 32-bit read from the memory, we are replicating the 8-bit 24 times. The higher 24 bit of the RT register is replaced with the 8th bit of the 32-bit data read from the memory. Okay, and lower 8 bit then is same as the LBU. You just pick up the lower 8 bit and replace the lower 8 bit of the RT. So that's signed load byte operation. Okay, so we have load word, which is doesn't care is signed or unsigned. It really depends on that whole 32 bit how we are using. Load, then we have load half word unsigned, load byte unsigned. So we are really loading an unsigned value in that notion. Then we have load half word signed and load byte signed. So you really need to use these carefully in your program depending on what type of value you are trying to handle, whether you are trying to handle an unsigned value or signed value, depending really on that. If you ever need to do an byte and half word operation, you should be careful about what you use. Do you use LBU or LB, LHU or LH? I believe throughout the class we don't really deal with that except for maybe exam questions. In assembly programming may not be, maybe for the experimentation, but not really for the project or programming assignment. I don't think it is there, but be sure to understand it, right? How these operate. Now let's look at the values stored. I have some values stored in the register. I want to store it into the memory address. So I can store couple of things, right? Word 32-bit, half word 16-bit, and byte 8-bit. And their mnemonics is SW, SH, SB. There is nothing like an unsigned part of it. There is nothing called unsigned signed notion because of the fact that we are just interested to like store a bit pattern. Okay, it is upon the usage of the bit pattern. When you load it back, then you want to think of this sign notion. Are you treating that 8-bit or 16-bit as a signed or unsigned? Only loading cares of this, right? In your programming, when you load some data from the memory, at that point only you are worried about the signed and unsignedness of certain sequence of bits. When you store, you just store that number of bit, and then you let the usage at the usage time to decide how to treat that 8-bit or 16-bit as an unsigned or signed value. Depends really on the program. So that's why store command doesn't have a, especially store half and store byte, does not have a corresponding unsigned part. It's just a pure bit pattern storage. And what it does, it basically take the content of the RT and memory address calculated by adding up content of RS and assign extension immediate, and in that address you store the complete word. Okay, again, as I mentioned, you calculate an address, and remember, from processor perspective, each address is a byte. Now SW is storing a word, so what will happen, these 4 byte in a word from will come to later, will come to how, what the sequence, like from lower byte to higher byte position or higher byte to lower byte position. That poses a interesting dilemma there, but let's for timing, let's assume these 4 bytes will be written into successive 4 addresses in a ascending order. Means you start with that address calculated by adding of content of RS and assign extension immediate, and then that goes the 1 byte, then plus 1 address goes a second byte, plus 1 another address goes a start byte, from there plus another address is goes a 4th byte. Okay, now store half word is the same thing. You go to one address, store 8-bit, a byte, and then one above you store another byte, another 8-bit. Okay, so that's what we do here. We take the lower 16-bit of the RT address, RT register, and store it into the address computed by adding of RS and assign extended immediate, and we store only 2 bytes there in this case, like, and store byte, we store a byte onto the computed address, and we pick up the lower 8-bit of the RT register.